What are possible next exciting directions to you in the space of MechInter?
Well, there's a lot of things. So for one thing, I would really like to get to a point where we have circuits, where we can really understand not just the features, but then use that to understand the computation of models. That really, for me, is the ultimate goal of this. And there's been some work. We put out a few things. There's a paper from Sam Marks that does some stuff like this. And there's been some, I'd say, some work around the edges here. But I think there's a lot more to do, and I think that will be a very exciting thing. That's related to a challenge we call interference weights, where due to superposition, if you just sort of naively look at whether features are connected together, there may be some weights that sort of don't exist in the upstairs model, but are just sort of artifacts of superposition. So that's a sort of technical challenge related to that. I think another exciting direction is just, you might think of sparse autoencoders as being kind of like a telescope. They allow us to, look out and see all these features that are out there. And, as we build better and better sparse autoencoders, get better and better at dictionary learning, we see more and more stars. And, we zoom in on smaller and smaller stars. But there's kind of a lot of evidence that we're only still seeing a very small fraction of the stars. There's a lot of matter in our neural network universe that we can't observe yet. And it may be that we'll never be able to find enough instruments to observe it, and maybe some of it just isn't possible, isn't computationally tractable to observe. And so there's sort of a kind of dark matter, and not in maybe the sense of modern astronomy, but of earlier astronomy when we didn't know what this unexplained matter is. And so I think a lot about that dark matter and whether we'll ever observe it, and what that means for safety if we can't observe it. If there's some significant fraction of neural networks are not accessible to us. Another question that I think a lot about is, at the end of the day, mechanistic interpretability is this very microscopic approach to interpretability. It's trying to understand things in a very fine-grained way. But a lot of the questions we care about are very macroscopic. We care about these questions about neural network behavior, and I think that's the thing that I care most about. But there's lots of other sort of larger scale questions you might care about. And somehow, the nice thing about having a very microscopic approach is it's maybe easier to ask, is this true? Mm-hmm. But the downside is it's much further from the things we care about. And so we now have this ladder to climb. And I think there's a question of, will we be able to find, are there sort of larger scale abstractions that we can use to understand neural networks? That can we get up from this very microscopic approach?
Yeah, you've written about this kind of organs question.
Yeah, so exactly.
If we think of interpretability as a kind of anatomy of neural networks, most of the circuits threads involve studying tiny little veins, looking at the small scale and individual neurons and how they connect. However, there are many natural questions that the small scale approach doesn't address. In contrast, the most prominent abstractions in biological anatomy involve larger scale structures like individual organs, like the heart, or entire organ systems like the respiratory system. And so we wonder, is there a respiratory system or heart or brain region of an artificial neural network?
Yeah, exactly. And I mean, like if you think about science, right, a lot of scientific fields have, investigate things at many levels of abstractions. In biology, you have molecular biology studying, proteins and molecules and so on. And you have cellular biology, and then you have histology studying tissues, and then you have anatomy, and then you have zoology, and then you have ecology. And so you have many, many levels of abstraction. Or, physics, maybe you have the physics of individual particles, and then, statistical physics gives you thermodynamics and things like this. And so you often have different levels of abstraction. And I think that right now we have, mechanistic interpretability, if it succeeds, is sort of like a microbiology of neural networks, but we want something more like anatomy. And so, and a question you might ask is why can't you just go there directly? And I think the answer is superposition, at least in significant part. It's that it's actually very hard to see this macroscopic structure without first sort of breaking down the microscopic structure in the right way and then studying how it connects together. But I'm hopeful that there is going to be something much larger than features and circuits, and that we're going to be able to have a story that involves much bigger things, and then you can sort of study in detail the parts you care about.
I suppose in neurobiology, like a psychologist or a psychiatrist of a neural network.
And I think that the beautiful thing would be if we could go and, rather than having disparate fields for those two things, if you could build a bridge between them, such that you could go and have all of your higher level abstractions be grounded very firmly in this very solid, more rigorous, ideally, foundation.
What do you think is the difference between the human brain, the biological neural network, and the artificial neural network?
Well, the neuroscientists have a much harder job than us. Sometimes I just count my blessings by how much easier my job is than the neuroscientists, right? So I have, we can record from all the neurons.
Yeah.
We can do that on arbitrary amounts of data. The neurons don't change while you're doing that, by the way.
Mm-hmm.
You can go and ablate neurons, you can edit the connections and so on, and then you can undo those changes. That's pretty great.
Yeah.
You can intervene on any neuron and force it active and see what happens. Which neurons are connected to everything, right? Neuroscientists want to get the connectome. We have the connectome, and we have it for much bigger than C. elegans.
Yeah.
And then not only do we have the connectome, we know which neurons excite or inhibit each other, right? So it's not just that we know that the binary mask. We know the weights. We can take gradients. We know computationally what each neuron does. So I don't know. The list goes on and on. We just have so many advantages over neuroscientists, and then, despite having all those advantages, it's really hard. And so one thing I do sometimes think is gosh, if it's this hard for us, it seems impossible under the constraints of neuroscience, or, near impossible. I don't know, maybe part of me is I've got a few neuroscientists on my team. Maybe I'm sort of maybe the neuroscientists, maybe some of them would like to have an easier problem that's still very hard. And they could come and work on neural networks. And then after we figure out things in sort of the easy little pond of trying to understand neural networks, which is still very hard, then we could go back to biological neuroscience.
I love what you've written about the goal of MechInter research as two goals: safety and beauty. So can you talk about the beauty side of things?
Yeah. So there's this funny thing where I think some people are kind of disappointed by neural networks, I think, where they're neural networks, it's these simple rules, and then you just do a bunch of engineering to scale it up, and it works really well.
Mm-hmm.
And where's the complex ideas? This isn't a very nice, beautiful scientific result. And I sometimes think when people say that, I picture them being evolution is so boring. It's just a bunch of simple rules, and you run evolution for a long time, and you get biology. What a sucky, way for biology to have turned out. Where's the complex rules? But the beauty is that the simplicity generates complexity.
Mm-hmm.
Biology has these simple rules, and it gives rise to, all the life and ecosystems that we see around us, all the beauty of nature. That all just comes from evolution and from something very simple in evolution. And similarly, I think that neural networks create enormous complexity and beauty inside it, and structure inside themselves that people generally don't look at and don't try to understand, because it's hard to understand. But I think that there is an incredibly rich structure to be discovered inside neural networks, a lot of very deep beauty, if we're just willing to take the time to go and see it and understand it.
Yeah, I love MechInter. The feeling we are understanding or getting glimpses of understanding the magic that's going on inside is really wonderful.
It feels to me like one of the questions is just calling out to be asked, and I'm sort of, a lot of people are thinking about this, but I'm often surprised that not more are, is how is it that we don't know how to create computer systems that can do these things, and yet we have these amazing systems that we don't know how to directly create computer programs that can do these things, but these neural networks can do all these amazing things. And it just feels like that is obviously the question that sort of is calling out to be answered. If you have any degree of curiosity, it's how is it that humanity now has these artifacts that can do these things that we don't know how to do?
Yeah, I love the image of the circuits reaching towards the light of the objective function.
Yeah, it's this organic thing that we've grown, and we have no idea what we've grown.
Well, thank you for working on safety, and thank you for appreciating the beauty of the things you discover. And thank you for talking today, Chris. This is wonderful.
Thank you for taking the time to chat as well.